The sun provides us with energy day in, day out. The energy that reaches the Earth on a sunny day is about 1000 watts per square meters, distributed over a certain spectrum of wavelengths. Using photovoltaic cells, it is possible to generate electricity out of the energy present in the sunlight. Of course, the supply of electric energy is highest in summer, when there is the most sun. The demand, however, is lowest at the same time, and when a lot of sun present, the supply might exceed the demand. So a lot of the possibly generated energy is wasted that could rather be used during times where the demand exceeds the supply, if there would be an adequate possibility of storing it. And that's where SHINE steps in. SHINE aims to take water and the energy present in the sunlight in order to store this energy by producing hydrogen. Of course, hydrogen generation is already easily possible. A basin filled with a liquid electrolyte, a membrane and 2 electrodes. When applying a voltage, H2O splits into H+ ions, electrons and oxygen on the anode side, while on the cathode side H+ ions and electrons provided by the electrode react and produce hydrogen. The major drawback of this is that the whole process in this simple form is not very efficient. The SHINE project aims to combine the expertise of its members in the 4 parts: hydrogen generation, solar concentration, photovoltaics integration and microfluidics. But the goal of the project is not to just combine optimized versions of these elements, but to rather create and optimize one device on the system level for a higher overall efficiency. Let's have a look at it in detail. For the hydrogen generation, SHINE will use a solid electrolyte called Naphthalene, coated with the catalysts and gas diffusion layers. Channels are added to allow the water vapor used as input feed to reach these gas diffusion layers. This forms the microreactor where, when a voltage is applied, oxygen and hydrogen are generated. However, the higher surface to volume ratio of the input feed and the electrodes and the use of a solid electrolyte make this cell much more efficient. To split water and generate hydrogen, a voltage of about 1.8 volt is required. In order to provide this voltage, a custom-tailored multi-junction cell is added at the cathode side. This solar cell consists of amorphous and crystalline silicon and is able to make efficient use of the solar spectrum. Since the P-junction of the solar cell is electrically connected to the anode of the electrolysis cell, incoming light will generate a voltage between the anode of the electrolysis cell and the N-junction of the solar cell. This voltage is set to exceed the voltage required for hydrogen generation due to the optimized design of the solar cell. To further increase the efficiency, these 2 elements will be used with a solar concentrator. The solar concentrator consists of a waveguide slab where concentration is achieved by having a large input aperture over a small exit aperture. The actuator consists of a metal housing filled with a mixture of paraffin wax and carbon black. On top of this is a PDMS membrane in which a dichroic prism array is embedded that reflects visible light and transmits the infrared. Above the waveguide, an array of lenses focuses the sunlight. As the sunlight is focused on the actuator, it is split in 2 parts: the reflected visible and the transmitted infrared. The infrared light is absorbed by the paraffin wax carbon black mixture, which heats up. Due to thermal expansion, it then expands upwards until the PDMS membrane touches the waveguide slab. This allows the visible light to be coupled into the waveguide, where the light is guided towards the solar cell by total internal reflection. Scaling the actuator down allows for multiple paraffin wax elements to be actuated at the same time. If now the sun moves during the day, the focus point of the lens will move accordingly, as does the coupling feature, which leads to a continuous coupling of sunlight into the waveguide. Of course, all of the lenses will couple light into the concentrator at the same time to achieve efficient concentration. Using photovoltaic cells with concentrated sunlight requires thermal management to keep it at optimal working temperature. The same applies for the phase change actuator. Therefore, microfluidic channels are added in between the solar cell and the waveguide, and below the phase change actuator. Water is now passed into the channel alongside the photovoltaic cell, cooling it down and in return increasing its own temperature. The heated water is then passed into the channels below the actuator. Here it takes up any excess heat, further increasing its temperature and turning into water vapor. This generated water vapor is then used as input feed for the photoelectrolysis cell, providing it with the feedstock it needs for efficient hydrogen generation, and thereby closing the loop between the four parts.